All right, we're back. We're going to be on page 3 of notes 13 of Calc C, talking about Euler's method, but we're going to take a little diversion and we're going to solve this differential equation because these are actually like the most common type you'll run into in AP calculus, and I think it's neat if you know how to solve them. Definitely not required for the AP exam, definitely not in the curriculum of a typical BC class, or AB, definitely not. But I think that it's accessible, and I think we should try to do it. So dy dx equals x plus y. And we're going to try to solve it. So here we go. So we have dy dx equals x plus y. So now the method we're going to use is going to look insane. And you're going to think like, how did anyone ever come up with this? Probably by observation, I guess. A surprising number of things in differential equations come down to like somebody noticed. So let's see. First thing we're going to do is we're going to bring the y over, just the y. So minus y is equal to x. So in doing that, I don't like that x. In doing that, we've sort of created a weird situation on the left-hand side, but you probably don't realize it. We have made a differential equation that looks like this. Dy dx equal, I'm going to say plus, I don't know, p of x times y equals, I'm going to say q of x, because you always got to use p's and q's together just to make it confusing, right? So we've got this. We have something that looks like this. If it is the case that these are equivalent, then p of x must be -1, and q of x is x, right, for our specific example. Here's what we're going to do. We're going to calculate or find e to the integral of p of x dx. Trust me on this. And this is called the integrating factor, which probably has like a fancy notation that I don't remember. It's probably a Greek letter. So that's going to be our integrating factor. And what we're going to do after we calculate it is we're going to multiply through by the integrating factor, and we'll see what happens. So first, let's calculate our integrating factor. So we're going to calculate e to the integral of -1 dx, which is e to the negative x. You don't do plus c's on this, just e to the negative x. Okay, so this is our integrating factor. And we want to take the integrating factor and multiply both sides of our differential equation by that. So we're going to multiply both sides by e to the negative x. So we have, maybe I'll use a different color for that. E to the negative x. I'm going to like cheat like a lot here and just duplicate some things. Dy dx. And then we have minus, I should have duplicated that when I had the chance. Duplicate minus, and then it'll be e to the negative x. Oh, wait, I took the y with, oh man, now they're in the wrong order. I mean, it's not like the wrong order, it's just like, you know, not the best order. Here we go, equals, and then on this side, we're gonna do it too. So I'll just write that e to the negative x. I think the x should probably go first. So we're moving stuff again, perfect. Okay, whew, that's what we have. Now, why did we do this? Well, I don't know if I'm writing general rules over here. So this is, this we need this, right? And then 1, we're going to find that. 2, we're going to multiply through by, let's abbreviate it as IF, the integrating factor. Okay, now, after we do that, 3, this is the mind-boggling part, but it's got to look like this. We need this to be true. If this is true, then when you multiply through by the integrating factor, the left side is the product rule. It will be, like, guaranteed. That's the method, product rule. Product rule, it's 2 words. There we go, product rule. That's like astounding. So let's see if that's true. Well, over here, it's like first derivative of the second plus second derivative of the first. It worked. So this side is d dx of e to the negative x times y. That's always going to happen. That's mind-boggling. So like the real key is, can you identify p of x successfully? E to the integral of p of x dx. And then it's going to be the product rule. And then since it's product rule, we should be able to integrate it, right? If you integrate a derivative, the notation here is like gross, and usually you just kind of like skip it. But I'm gonna press on and regret it, but doing it. And here, because on the left-hand side, you just have like x's and y's, and it's like gross, and you shouldn't really use that notation. But I think it's a no harm, no foul thing. Integral of a derivative should just take us back to the original. And then on this side, integration by parts, super. I'm gonna use a table because it's like real fast. Oh, I'm not using a table, it turns out. I don't know, I wanted to, but like, you know, my hand didn't. So du is gonna be dx v negative e to the negative x. All right, excuse me. So we have, I might need to move that. We have uv, so negative x e to the negative x minus the integral of v to u. So that'll be plus the integral of e to the negative x dx. Okay, and then we integrate one more time. This is why I should have used a table, but it's all right. I get negative e to the negative x. That's a terrible negative sign. And then plus c. So plus c is really important on this part. You have to put plus c because we're about to divide through. You got to solve for y, right? Solution to differential equation. Solve for y. We're going to divide by e to the negative x. When you divide c by e to the negative x, it does not become c again, right? You can't absorb a function. You can absorb a constant. You can do c divided by 5 is just a new value of c. This we have to keep. So this is going to be y equals. So e to the negative x will cancel here. We just get negative x. E to the negative x will cancel here. We just get minus 1. And then we get plus c over e to the negative x, which I'm going to write as ce to the negative x. So this is really because we had c over e to the negative x. Oh, so I'm wrong. So we have ce to the x, not e to the negative x. So we have this. This is pretty neat. If you remember, which like, I feel like it's probably pretty dicey on you remembering this. These sorts of differential equations, the dy dx equals x plus y, they always have like a linear solution kind of running through them. And you could kind of guess the linear solution, especially from the slope field. It turns out now we know how to solve it. Use this integrating factor method. So what I'm going to do, wow, that didn't use a lot of, I'm going to use the calculator, desolve, and just take a look at this. This is a method. This will work anytime you have a differential equation that's of the form dy dx plus p of x times y equals q of x. It's always going to work. Calculate your integrating factor, you're good to go. I'm going to start a new document just because. So calculator, desolve, and then it's y prime equals x plus y, comma x, comma y. So you get negative x minus 1 plus ce to the x. Let's look at the slope field for that, just to, I don't know, for completeness or something. So menu, option 3, differential equation, x plus y1, just gonna graph it. Let's change, let's click the 3 dots and change our field resolution to like 20 and say okay. All right, I think that looks a little better. I'm gonna switch back to function mode, and then I'll graph, I'm just gonna graph negative x minus 1, so like the slant asymptote of this thing. And it's a perfect fit, right? And then you can just play around with you know, your values. So it's like negative x minus 1 plus c times e to the x. Let's do such that c equals, you can feed it like a couple different c values. So like negative 3, negative 1, 3, and 1, let's say. I don't know why I'm doing those values, but whatever. And also the order, what? Create a slider, I don't want that. Look at that, we get a solution that's decreasing concave down, a solution that's concave up and always has a relative minimum, and then we also get the linear solution. Excuse me. So we did it. It's a really neat process. Integrating factor, always going to work on those. Very cool. Integrating factor doesn't work on every type of differential equation. So like separation of variables doesn't work on every type of differential equation. This is how differential equations work. You have a specific form, and there's a specific way to solve it. And so the integrating factor will work on these, but not necessarily others. Separation of variables works on some, but not necessarily these, and so on. And you got to expand your toolbox so that you have all the ways you can solve them. I'm going to end this here. I will come back in the next video and do some more. So I will see you there.